Hello friends, nice meeting you. We want to discuss today the problem of autocorrelation. Generally, when we consider linear model, then the disturbances are not correlated. Also, they are not correlated with the explanatory variables. But sometimes it happens that the disturbances themselves are correlated by means of some serial correlation. So, such problem will be called problem of autocorrelation, and we want to study this in detail. So, first of all we should know what are the tests of autocorrelation. Once we know this test, then we should know how we can tackle the problem of autocorrelation, and that is how we can deal with this situation whenever it occurs in practice. So, now we will study this in detail.
Hello friends, today we are going to discuss autocorrelation. What is the problem of autocorrelation? While dealing with GLM, one of the basic assumption was about homoscedasticity, that is uniform variance for the disturbances, and pairwise the disturbances are uncorrelated. If we violate this condition of uniform variance of disturbances and pairwise statistical independence among disturbances, we have the phenomena of heteroscedasticity. In addition, if we put the condition that any pair of disturbances is serially correlated, then this phenomena is called autocorrelation. Before we go into further details, let us know about the nature of disturbances as shown by the diagram. We may plot U or U cap, that means E, against time. We can have different situations as shown here. Figure A shows that there is a cyclic pattern. Figure B shows that there is an upward linear trend. Figure C shows that there is a downward linear trend. Figure D shows that there is both a linear and quadratic trend, and figure E shows that there is no such pattern. Here, figure A to figure D exhibits that there is some sort of autocorrelation between disturbances, and figure E shows that there is no autocorrelation among the disturbances. Briefly, we may say that in figure A to figure D, the disturbances are seen to be serially related. Number 2. What are the reasons for autocorrelation? Some reasons for observing autocorrelation can be briefly summarized as: number 1. Inertia. In some time series like GNP, production, employment, etc., the series moves steadily up or down. But in the longer span period, the series remains almost stagnant or steady, and then it starts ahead. This is called inertia, and it causes autocorrelation. Number 2. Manipulation of data. Due to interpolation and extrapolation based upon time series data, it is observed that the data are manipulated. Many times the quarterly data on time series are obtained by aggregating the data for 3 months to visualize quarterly variation. This is called smoothing of the time series data, which cause autocorrelation. Number 3. Specification bias. When one or more variables are excluded from the model, we have the problem of specification. As per example, we have the model yt equal to beta 1 plus beta 2 x2 t plus beta 3 x3 t plus beta 4 x4 t plus ut. Now, if we exclude x4 t from the model and write yt equal to beta 1 plus beta 2 x2 t plus beta 3 x3 t plus vt, then actually vt equal to beta 4 x4 t plus ut. If we write disturbances term as ut alone, it is a specification bias which causes error due to autocorrelation. Number 4. Incorrect specification of the model. Sometimes incorrect specification of the model also causes autocorrelation. For example, we have the model yt equal to beta 1 plus beta 2 xt plus beta 3 xt square plus ut. If we write it as yt equal to beta 1 plus beta 2 xt plus vt, then actually vt equal to beta 3 xt square plus ut. So, if we treat disturbances as ut alone, then it is not proper. This is also specification bias which leads to the presence of autocorrelation. Number 5, cobweb phenomena. Cobweb model represent the supply at time t in terms of the price at time t minus 1. But if the price at time t is more or less than the price at time t minus 1, then accordingly supply will change, and that in turn results in change in price and so on. Due to such cobweb phenomena, the effect will be to change the disturbances so that we find the presence of autocorrelation. Number 6, due to lag structure in the model. Consider a model as Ct equal to beta 1 plus beta 2 It plus beta 3 Ct minus 1 plus Ut, where Ct equal to consumption at time t, It equal to income at time t, and Ct minus 1 equal to consumption at time t minus 1. Here there is a lag in the model. Current consumption is affected by earlier consumption. Note that one of the explanatory variable is the dependent variable in the earlier period. If this fact is neglected, then it is resulting effect will be on the autocorrelation. Number 3, what are the practical consequences of autocorrelation? We want to illustrate the case for the presence of autocorrelation by means of our two variable linear regression model. We write this model in the standard form yt equal to beta 1 plus beta 2 xt plus ut, where t equal to 1, 2 up to n. We denote it as equation number 1. Along with the usual assumptions for this model, we impose some more condition for the disturbances in the model. We assume that ut equal to rho ut minus 1 plus epsilon t, where t equal to 1 to up to n, and we denote it as equation number 2, which shows that the disturbances ut follows first order autoregressive scheme. Here rho is called coefficient of autocovariance or autocorrelation or autocorrelation coefficient, where minus 1 less than or equal to rho less than or equal to 1 and epsilon t is the stochastic disturbance term. We further state that epsilon t satisfied the assumptions expected epsilon t equal to 0 for all t, variance of epsilon t equal to expected epsilon t square, which is equal to sigma square for all t, covariance of epsilon t and epsilon t plus s equal to 0 for all t where s is not equal to 0. We denote it as equation number 3. Thus, expected value of epsilon t point epsilon t plus s equal to sigma square if s equal to 0, and if s is not equal to 0, it is 0. Note that stochastic disturbance term epsilon t satisfies all the basic assumptions for standard model. For equation 2, ut equal to rho ut minus 1 plus epsilon t. We take by simplification rho multiplied by rho ut minus 2 plus epsilon t minus 1 plus epsilon t, which equals to rho cube ut minus 3 plus rho square epsilon t minus 2 plus rho et minus 1 plus epsilon t, and so on. This is show that ut equal to epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus rho cube epsilon t minus 2 plus so on up to infinity. Hence, ut equal to summation j equal to 0 to infinity rho raised to j multiplied by epsilon t minus j. Thus, expected ut equal to summation of rho raised to j expected of epsilon t minus j, which is equal to 0 for all t. Now, ut square equal to epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus rho cube epsilon t minus 3 plus so on whole square. Hence, expected ut square equal to expected epsilon t square plus rho square multiplied by expected epsilon t minus 1 square plus rho raised to 4 expected epsilon t minus 2 plus so on. Since expected epsilon t square equal to sigma square for all t, we get expected ut square equal to sigma square multiplied it by 1 plus rho square plus rho raised to 4 plus up to infinity, which is infinite geometric series. Hence, variance of ut equal to sigma square upon 1 minus rho square, which is equal to sigma u square. expected ut point ut minus 1 equal to rho sigma square, expected ut point ut minus 2 equal to rho square sigma square up to so on, expected ut point ut minus s equal to rho raised to s multiplied by sigma square. We define rho s equal to serial correlation coefficient of order s, which is correlation coefficient between ut and ut minus s. Then rho s equal to covariance of ut and ut minus s whole divided by under root of variance of ut multiplied by variance of ut minus s. After simplification, we get rho s equal to rho raised to s. This is relation for serial correlation coefficient of order s in terms of the autocorrelation coefficient. Note that for s equal to 1, rho 1 equal to rho. Thus, serial correlation coefficient of first order is the autocorrelation coefficient. Hence, in practice, we may use both the words conveniently. Thus, the dispersion matrix for the disturbances will be given by variance of vector u, which is equal to expected u vector and u dash vector, which is equal to v, where v is given by the following matrix. Here sigma u square is the variance of u, which given by sigma u square equal to sigma square upon 1 minus rho square. For example, for 4 variables model, v equal to sigma u square multiplied by the matrix having the diagonal element 1 1 1 1 and the other element rho, rho square, rho cube and so on, which is a real symmetric matrix with all the elements in the principal diagonal as unity. We may compare these situations by using OLS and GLS method. Model y vector equal to x beta vector plus u vector. For GLS, expected u vector equal to 0 vector and for OLS, expected u vector equal to 0 vector. For GLS, variance of u vector equal to sigma u square multiplied by v, and for OLS, variance of u vector equal to sigma u square multiplied by in. For GLS, rho x equal to k less than n, and for OLS, rho x equal to k less than n. For GLS, beta g cap vector equal to x dash v inverse x whole inverse x dash v inverse y vector. For OLS, beta cap vector equal to x dash x inverse x dash y vector. For GLS, expected beta g cap vector equal to beta vector, and for OLS, expected beta cap vector equal to beta vector. And for GLS, variance of beta g cap vector equal to x dash v inverse x whole inverse sigma u square, and for OLS, variance of beta cap vector equal to x dash x inverse sigma u square. Note that if v equal to in, GLS and OLS are exactly identical. Now we consider the phenomena of autocorrelation where u's are autocorrelated as shown. So here if we use OLS method for estimation, then beta cap vector equal to x dash x inverse x dash y vector, which is equal to x dash x inverse x dash multiplied by x beta vector plus u vector, which gives beta vector plus x dash x inverse x dash u vector. Thus, beta cap vector minus beta vector equal to x dash x inverse multiplied by x dash u vector. Variance of beta cap vector equal to expected value of beta cap vector minus beta vector multiplied by beta cap vector minus beta vector dash. By simplification, x dash x inverse multiplied by x dash expected of u vector multiplied by u dash vector, multiply it by x dash x inverse. Variance of beta cap vector equal to x dash x inverse x dash v x dash x inverse, where matrix V is as indicated above under autocorrelation phenomena. If V equal to sigma u square in, then variance of beta cap vector equal to x dash x inverse sigma u square. However, if we use GLS estimator, then variance of beta g cap vector equal to x dash v inverse x whole inverse multiplied it by sigma u square. Here it may be worthwhile as to which estimator can be considered to be preferable. Note that due to matrix V, we may have the estimator with larger variance, but this all depends upon the autocorrelation coefficient. Generally, variance beta cap vector under autocorrelation will be larger than that without autocorrelation. We want to understand this by means of two variable model. we denote the model by yt equal to beta xt plus ut, where t equal to 1 to up to n, where the original variables are deviated from their means. Thus, we consider the reduced form. We have the relation ut equal to rho ut minus 1 plus epsilon t for the case of autocorrelation. In matrix notation X having the order n cross 1, x1, x2 up to xn, hence x dash x inverse equal to 1 upon summation 1 to n xi square and beta caps vector equal to beta cap. Thus, using the relation variance of beta cap vector equal to x dash x inverse x dash vx x dash x inverse, we get variance of beta cap equal to 1 upon summation xi square multiplied it by x1 x2 up to xn multiplied by v multiplied by vector x1 x2 up to xn multiplied by 1 upon summation xi square, which gives after some simplification the result is variance of beta cap equal to sigma u square upon summation xi square multiplied by 1 plus 2 rho in bracket summation 1 to n minus 1 xi multiplied by xi plus 1 upon summation 1 to n xi square plus 2 rho square multiplied by summation 1 to n minus 2 xi into xi plus 2 upon summation 1 to n xi square plus up to so on plus 2 rho n minus 1 multiplied by x1 xn upon summation 1 to n xi square. Check that when rho equal to 0, that is when there is no autocorrelation, we get variance of beta cap equal to sigma u square upon summation xi square as before. Let us suppose that rho greater than 0 and also that x's are autocorrelated with autocorrelation coefficient rho, then we can write rho equal to summation 1 to n minus 1 xi multiplied by xi plus 1 upon summation 1 to n xi square. Rho square equal to summation 1 to n minus 2 xi multiplied by xi plus 2 divided by summation xi square and so on, and finally we get rho raised to n minus 1 equal to x1 xn upon summation xi square. So that after some simplification we get the expression in the case of sufficiently large n. Variance of beta cap approximate sigma u square upon summation xi square multiplied by 1 plus rho square upon 1 minus rho square greater than sigma u square upon summation 1 to n xi square. Since rho greater than 0, 1 plus rho square upon 1 minus rho square greater than 1. Hence, we may conclude that variance will be larger in the case of autocorrelation as compared to that in the case of no autocorrelation. Thus, we conclude that if we ignore the phenomena of autocorrelation, variance of the estimator remains underestimated. Estimation of sigma cap square in the case of autocorrelation. We know that for two variables model under no autocorrelation, sigma cap square equal to summation 1 to n ei square divided by n minus 2. In the case of autocorrelation, it can be shown that the estimation of sigma square is given by the formula expectation of sigma cap square equal to sigma square multiplied by n minus 2 upon 1 minus rho minus 2 rho r whole divided by n minus 2, where r equal to summation 1 to n minus 1 xi multiplied by xi minus 1 whole divided by summation 1 to n xi square, and rho equal to autocorrelation coefficient. This also indicates that under autocorrelation the variance gets underestimated. From the above expressions that we have studied, it is apparently useful and important to detect the presence of autocorrelation in the model when we deal actually with our data analysis. Our next two sections will consider this important aspect of detecting the problem of autocorrelation, and hence after tackling the problem of autocorrelation. How to detect autocorrelation? Number 1, graphical method. As already explained earlier, we can detect the autocorrelation situation by plotting the values of u or u cap against time t. However, this method just gives some preliminary knowledge only, but for more exactness, we have to use the test for autocorrelation. Number 2, certain test for detecting autocorrelation. Number 1, von Newmann ratio test. Here, we want to test the hypothesis. Our null hypothesis is rho equal to 0 against alternative hypothesis rho not greater than 0, where rho equal to autocorrelation in the given series. Von Newmann considered the ratio also known as VNR, which is given by VNR equal to capital delta, which is equal to delta square upon S square, which is equal to summation I from 2 to n EI minus 1 square divided by n minus 1 whole divided by summation I 1 to n EI minus summation I 1 to n EI minus E bar whole square divided by n, where E bar equal to summation I 1 to n EI upon n, EI equal to ith error term. It can be shown that for large samples, expected delta equal to 2n upon n minus 1, which is equal to mean value of delta. Variance of delta equal to 4n square multiplied by n minus 2 whole divided by n plus 1 multiplied by n minus 1 whole square, which is equal to variance of delta. Then we can apply normality test given by modulus of z equal to modulus of delta minus expected delta whole divided by square root of variance of delta. Hence, if modulus z is significant, reject null hypothesis, which means that there is autocorrelation. This can be tested as usual at 5% as well as 1% level of significance. Durbin-Watson test, which is also known as DW test. Number 1, assumptions. The assumption 1 is regression model assumes the intercept term. If the deviated form is used, compute the error term based upon the regression with intercept term. Number 2, the explanatory variables are non-stochastic or fixed in the repeated sampling. Number 3, the disturbances ut are generated by the first order autoregressive scheme given by the equation ut equal to rho ut minus 1 plus epsilon t. Number 4, regression model does not include lagged value of the dependent variable as one of the explanatory variable. Number 2, test statistic. Define statistic D given by the formula D equal to summation I 2 to n EI minus 1 whole square whole divided by summation I from 1 to n EI square. Here EI equal to ith error term in the sample of n observations. The exact distribution of D is difficult due to expression on the right hand side because the errors depend upon the explanatory variables. Derby and Watson have obtained a lower bound DL and upper bound DU to apply this test for detecting serial correlation in the given series. For example, null hypothesis is rho raised to s equal to 0, which implies rho equal to 0 for all s. Writing D equal to summation I 1 to up to n EI square plus summation I 2 to n EI minus 1 square minus 2 summation I equal to 2 to n EI multiplied by EI minus 1 whole divided by summation I from 1 to up to n EI square. Since only one observation is missing in the numerator, we can set summation I 1 to up to n EI square approximately equal to summation I from 2 to n EI minus 1 square. This shows that D approximately 2 1 minus summation I 2 to n EI minus 1 divided by summation I from 1 to up to n EI square. Let us denote sample first order autocorrelation coefficient by rho star equal to summation I from 2 to n EI minus 1 whole divided by summation I from 1 to up to n EI square. Then D is approximately 2 1 minus rho star. Number 1, if rho star equal to 0, D is approximately 2. If rho star equal to 1, D is approximately 0. If rho star equal to minus 1, D is approximately 4. Hence, D lies between 0 to 4. Working rule number 1. If D is very near to 2, there is no positive autocorrelation. Number 2. If D is very close to 0, there is positive autocorrelation. We can say perfect if D equal to 0. Number 3. If D is very near to 4, there is negative autocorrelation, that is perfect if D equal to 4. Computational procedure. Run the OLS regression as usual and obtain the residuals. Compute D statistic by the formula as given. Number 3. For the given sample size n and the given number of explanatory variables k, obtain value of DL and DU from the tables prepared by DW, that is DW test tables. Different tests can be considered as shown below. Diagrammatic presentation helps in locating the test procedure. Here, null hypothesis is no positive correlation, and alternative hypothesis, which we denote as H naught star, no negative correlation. Decision rules. If our null hypothesis is no positive autocorrelation, then our decision is to reject the null hypothesis if our D lies between 0 to DL, and further null hypothesis can be tested by using Number 1. This test is very popular for all applications. Number 2. To overcome the problem when decision cannot be taken due to indecisive region, modified DW test can be used. Number 3. There are other tests also for detecting autocorrelation. They are named as Run test, Durbin's H statistic test, Bruce-Godfrey, that is BG test of higher order autocorrelation, Durbin M test, etc. Number 4. For DW test, the sample size should be as least 15. What are the remedial measures to tackle the problem of autocorrelation? Case number 1. When rho is known. Method 1. Method of generalized difference equation. Consider the two variables model yt equal to beta 1 plus beta 2 xt plus ut. We denote it as equation number 1. And ut equal to rho ut minus 1 plus epsilon t, we denote it as equation number 2, where modulus of rho less than 1. Here yt minus 1 equal to beta 1 plus beta 2 xt minus 1 plus ut minus 1. Rho yt minus 1 equal to rho beta 1 plus rho beta 2 xt minus 1 plus rho ut minus 1, which gives generalized difference equation 3. Yt minus rho yt minus 1 equal to beta 1 1 minus rho plus beta 2 xt minus rho xt minus 1 plus epsilon t. We denote it as equation number 3, where epsilon t equal to ut minus rho ut minus 1. Since epsilon t satisfy all the assumptions for OLS, we can run this regression given in equation number 3. Here, due to differences on observation on x and y is lost. To avoid this, we can transform the first observation on y as y1 multiplied by under root of 1 minus rho square, and first observation on x as x1 multiplied by under root of 1 minus rho square, which solves the difficulty. Note, how to know rho? Number 1. Since d is approximately 2 multiplied by 1 minus rho, which implies rho approximately 1 minus d by 2, which gives the value of rho for large samples. Number 2. We can use Thel-Nagar formula for obtaining rho for small samples, where rho cap equal to n square multiplied by 1 minus d by 2 plus k square whole divided by n square minus k square. Here n equal to sample size and d equal to DW statistic, k equal to number of coefficients including intercept. Case 2. When rho is unknown. Number 1. First difference method. Let yt equal to beta 1 plus beta 2 xt plus ut. Then yt minus 1 equal to beta 1 plus beta 2 xt minus 1 plus ut minus 1. So, delta yt equal to beta 2 delta xt plus epsilon t, where epsilon t equal to ut minus 1. This equation can be regressed. Note that there is no intercept term here. Similarly, if original equation is yt equal to beta 1 plus beta 2 xt plus beta 3 t plus ut, then delta yt equal to beta 2 delta xt minus 1 plus beta 3 plus delta ut. Here coefficient of t, that means beta 3, becomes intercept term in the transform model. Run this regression as usual. Number 2. Moving average regression model, which is also known as MAR model. Consider the generalized difference equation GDE given by yt minus rho yt minus 1 equal to beta 1 multiplied by 1 minus rho plus beta 2 multiplied by xt minus rho xt minus 1 plus epsilon t. If we assume that rho equal to minus 1, that means there is perfect negative autocorrelation, then the above equation gives yt plus yt minus 1 divided by 2 equal to beta 1 plus beta 2 multiplied by xt plus xt minus 1 divided by 2 plus epsilon t divided by 2. This moving average regression model using 2 periods as periodicity to work out. Run this regression as usual. Note, this method work out if rho equal to minus 1. We need to test whether rho equal to minus 1 or not. For that, there is an advanced method known as Baron-Blunt-Webb BW test. Number 3. Cochran-Orcutt iterative procedure. Consider the model yt equal to beta 1 plus beta 2 xt plus ut. We denote it as equation number 1 with autoregressive AR scheme given by ut equal to rho ut minus 1 plus epsilon t. We denote it as equation number 2. And as in earlier case, we have GDE given by yt minus rho yt minus 1 equal to beta 1 multiplied by 1 minus rho plus beta 2 xt minus rho xt minus 1 plus ut minus rho ut minus 1. We denote it as equation number 3. Here beta 1 beta 2 rho all are unknown. We apply the iterative procedure as number 1. Run the regression equation 1, find OLSE of beta 1 and beta 2 and hence find ut cap. Number 2. Now using values of ut cap, run the regression number 2 and estimate rho given by rho 1 cap. Ut cap equal to rho cap multiplied by ut minus 1 plus ut. Number 3. Now run the regression 3 using rho 1 cap obtained as above. We write equation 3 as yt star equal to beta 1 star plus beta 2 star multiplied by xt star plus et star. Here beta 1 star equal to beta 1 multiplied by 1 minus rho 1 cap. This regression gives beta 1 cap star and beta 2 cap star. Hence we put in equation 1 and get new residuals, that is ut double star equal to yt minus beta 1 cap star minus beta 2 cap star xt. We denote it as equation number 4. This can be obtained easily as now yt, xt, beta 1 cap star and beta 2 cap star are known. Number 4. Now use equation 2 again to obtain new value of rho cap denoted by rho 2 cap using the relation ut double star equal to rho 2 cap multiplied by ut minus 1 double star plus wt. We denote it as equation number 5. This is second round estimate of rho given by rho 2 cap. Compare rho 2 cap with rho 1 cap. If they are very near, our procedure stops here. The difference should be by less than 0.01 or 0.005. Number 5. If rho 2 cap differs largely from rho 1 cap, repeat the above stated procedure. Thus we get successive iterations which give us final outcome. Note, number 1. The above iterative procedure ends in a finite number of steps. We can compute D and test about autocorrelation. Number 2. Besides this method, there are other models also which are named as number 1. Cochran-Orcutt two-stage iterative procedure. Number 2. Durbin's two-step method of estimating rho, etc. Number 3. All these methods work out in 2 or 3 stages. In literature, these methods of estimation are called feasible or estimated generalized least squares, that is EGLS methods. Thank you.